Hey y'all, welcome back to another exciting round of chemistry notes. Today we're going to talk about accuracy, precision, and percent error. And this video is so important because these are all year skills that we're learning. These are things you're going to use from now until May in lab reports, on tests, all over the place. Super important stuff today. So these terms, accuracy and precision, you've probably heard at some point in your life before, maybe in a scientific context, maybe just in regular conversation, but we're going to flesh them out a little bit and make them more specific to our class. So our first word here is accuracy. Pardon the lines, they're going to happen a lot. Accuracy is the closeness of measurements to the correct or accepted value. And as far as we are concerned in this class, the magic number is 5%. We're going to talk about percent error a little bit later in this video. And when we do this, will make a little bit more sense. But on lab reports, on tests, if I say, was this result accurate? You're going to check the percent error. And if the percent error is less than 5%, then yeah, it was accurate. Good job. Our measurements were close to the correct or accepted value. Another way to look at this is just how close the measurements are to the truth. So if your realm of possible answers was a target, your accuracy, how close you were to the truth, would be how close you are to the bullseye. If you get a bullseye, you are accurate. And if you are off the target entirely, you are not accurate. So that's going to help us visualize this a little bit. Our second word we're going to talk about is precision. This one you might be a little bit less familiar with, but precision is the closeness of a set of measurements of the same quantity made in the same way. We are doing the same thing over and over, taking the same measurement several times. How well did we do it? How close were our measurements to each other? Because precision is how close your measurements are to each other. Are you doing it the same way every time? Can your results be trusted? Ideally, your measurements should be within 0.2 of each other. This number is not quite as important as the 5% number. This is the one we really care about up here. So putting this into a more visual context, we're going to look at 4 different targets. Here in round 1, we've got our 4 trials, our 4 measurements here. And as you can see, they really don't cover a huge portion of the target. If we fill in this space between them, we're not filling in a really big space. But the space that we fill is right in the center of the bullseye. So the fact that all of our measurements are very close to the bullseye, very close to the truth, that means that, yeah, this is accurate. We did a good job. Our answers were close to what they should have been. And the fact that this area between them is very, very small, the fact that they're very close together, means that this is also precise. So this is the golden standard. If you can do this every time, get precise answers and accurate answers, that's ideal. You are doing a great job. Probably won't happen every time. That's okay. Looking at our next round here, we've got a similarly small area here. If we shade in between all of our trials again, all of our measurements, they still don't cover a very large portion of the target, but our bullseye is over here and our measurements are over here. So they're not really close to the bullseye. They're not really close to the truth. They're not close to that real value that we're looking for. So these are not accurate. But since they're all still so close together, we can be pretty certain we did this the same way every time. We had the same method for our same measurements, so it was precise. Looking at round 3, now we've got something a little different. If we fill in this space between them, they are much more spread out this time. This area between them is much, much larger. And as we fill it in, we can see that even though we're covering a very large portion of this target, we're still not covering the bullseye. So the fact that as a whole, these were not very close to the target means that this was really not very accurate at all. It was not accurate. And because they're so spread out, they're so far apart, it's pretty clear we were not doing this the same way every time. This is not precise either. This is sort of a worst case scenario. It's not precise, it's not accurate, we were wrong, and we weren't even wrong in the same way every time. This is really less than ideal. And our last round here, we have, once again, our 4 trials, and if we fill in, again, we can see that they're filling in a pretty large portion of our target here, but this time, if we fill in the space between them, we are actually covering up the bullseye. So this is kind of a weird scenario. This is kind of the hardest one to wrap your mind around, but this is technically accurate, because if you took an average of all of these trials, if you took the center of all of these measurements, all of these temps, you are going to end up in the bullseye. So this one is kind of the weird scenario, because each of these attempts are fairly far from the bullseye, fairly far from our intended value, but if we average them out and look in the center, we're going to end up with the correct value. So actually this is accurate. It's just that it's not at all precise. They're so spread out that clearly something different was happening every time, and we just happened to get the correct value there in the middle at some point. So this is what it looks like to be accurate, but not precise. Obviously, you're not going to be seeing a lot of bullseyes in chemistry class, so let's look at a more topical example to us. This example is talking about Wayne and Bruce, who measured the length of a pencil 3 times, multiple trials. Good job, Wayne and Bruce. And they got the following data. The manufacturer says that the length of the pencil is 19 centimeters. So this is our truth. This is our bullseye. This is what we are trying to find when we are measuring. So then if we go ahead and look at their measurements, Wayne got 19.0, 18.9, and 19.1. Bruce got 18.2, and then 18.2 again, and then 18.2 again. So looking at each measurement, in measurement 1, Wayne was quite a bit closer. Wayne actually hit the accepted value. Bruce, not that close. Looking at measurement 2, Wayne was not quite on the accepted value, but very, very close. Bruce, not so much. And in measurement 3, Wayne overshot the accepted value just a little bit, but again, compared to Bruce, very close. So this first question says, who had the most accurate measurements? Well, you can see that Wayne was much, much closer to that truth, to that accepted value, to that bullseye. So Wayne had the more accurate results. His were closer to the right answer. The next question says, who had the most precise measurements? Again, we don't even have to know that the pencil was actually 19 centimeters to answer this question, because the precision, the most precise measurements, are just the ones closest to each other. So looking here again, Wayne never got the same number twice, but Bruce, he got the same number all 3 times. He was not doing the right thing, but whatever he was doing he was doing very well. So definitely Bruce had the more precise measurements here. Good job, Bruce. All right, so the last topic we need to talk about in this video is percent error. We touched on it earlier. And percent error is calculated by subtracting the accepted value, that bullseye value, that truth, subtract that from the experimental value, subtract that from whatever you found, and then divide that difference by the accepted value, again, by that truth value. And then because it's a percent, you're going to want to multiply it by 100. So again, putting that into something a little easier to look at, we have this formula right here. This is your percent error formula, and this is one of the few formulas that is not going to show up on your formula chart. So this guy right here, you need to memorize this. Know it, love it, it's your new best friend. You need to know this. Accepted minus experimental divided by accepted times 100 gives you percent error. If it helps, the subtraction goes in alphabetical order. Accepted minus experimental. And then you always want to divide by the accepted value, because even if you completely screw up your experimental value, which does happen, you're still dividing by the same accepted value every time. So breaking this down a little bit more, that accepted value, again, that's the correct value. That is the true value. It's the truth. It's the bullseye. It's the golden standard. It's what you want to get. Then you have your experimental value. That is what happened in your experiment. It's what you got as your data, as your measurements. It's what you found when you did this. So If you have a percent error that is positive, it means that the accepted value was greater than the experimental value. When you measured that pencil, when you measured whatever it was you were measuring, the number you got came up a little bit short, and that's going to give you a positive percent error. On the flip side of that, if you have a negative percent error, it means that the number you got was a little bit too big. Your experimental value is bigger than the accepted value. So, putting this into practice, doing a couple of examples here. Example number 1 says to calculate the percent error in an experimental mass measurement of 5 grams if the accepted value is 10 grams. So again, this is what we found. This is our data. And this is what the actual number is. This is the truth. So we're just going to plug that straight in to that percent error formula, which again, you need to memorize. It will not be given to you. So we have percent error is equal to, we'll do our accepted value of 10 grams minus our experimental value of 5 grams. Divide all of that by the accepted value, that 10 grams again. And then because it is a percent, we will do times 100. Breaking this down just a little bit, always safer to do it in steps. If you have even the smallest question about your processing skills into the calculator, go ahead and just do it in stages. We have 10 minus 5 is 5 grams over 10 grams times 100 gives us 0.5 times 100. Notice that the grams here cancel out, units go away, giving us a percent error of 50%. So at this point, ask yourself, was this an accurate measurement? Was our percent error less than 5? Not even close. A resounding no. This was not an accurate experiment. We need to revisit what we did, try something different. Let's look at example number 2. Example number 2 says a teacher calculates the molar mass of sodium hydroxide as 37 grams per mole. A lot of this looks unfamiliar. We're going to learn this very soon, so get excited. So the teacher calculated 37. The true molar mass is 40 grams per mole. So again, this is our experimental value here, and this is our accepted value here. And we want to find the percent error. Notice that this time we're not looking for a final answer, we're looking for the correct setup down here. So we can go ahead and set it up ourselves and then just see which one matches. That tends to be the safest way to do it. So we'll do, once again, our accepted value of 40, so 40, minus our experimental value of 37, divided by that accepted value of 40, times 100. And none of our answer choices look like that. Looks like we need to do one more step, right? So we'll say this is the same as 40 minus 37 is 3, divided by just 40, times 100. And if we look down here, obviously these have units in the answers, but as far as numbers go, we have 3 over 40 times 100, 3 over 40 times 100. Answer choice C was the teacher's percent error. All right, let's go through one more together, and then y'all will have a chance to practice on your own a little bit. So example number 3 here. There are 34 questions on a test. Alfred answers 22 of them correctly. What is Alfred's percent error? So this one is a little different. It doesn't straight up say, here's experimental, here's accepted. You have to reason through it a little bit. But it's expected that you should get 100% of the questions correct, right? If there are 34 questions on a test, that's the ideal value. That's what you're shooting for. So this is going to be our accepted value. Because in a perfect world, this is how many questions we'd get right on a test. Alfred didn't quite get there. He got 22 of them correct. So this is our experimental value. because this is what he got when he actually went and took that test. So setting this up in our equation once again, we have percent error is equal to that accepted value of 34 questions minus that experimental value of 22 questions divided by, again, the accepted value of 34, and then multiply that by 100. So then once again, solving this through, 34 minus 22 is 12 over 34 times 100. Solving that through the rest of the way, you should end up with 35% error. So once again, Alfred, not super accurate on his test. Don't be like Alfred. Study for your test. At this point, there is some practice in your booklet for you to work on. Practice makes perfect. The more you practice, the more perfect you will be. Go ahead and take a minute, pause this video, work through those practice problems, and then unpause the video to check your answers. All right, hopefully this is what you ended up with on those next 3 problems. If you did not get these as your answer, there's a more detailed answer key on my website. Go ahead and head over there, check it out, see where you went wrong. If you did get this, congratulations, that's awesome. And now you are more than ready to proceed on to your quest assignment and work on some of those problems. If not, go back through your practice again, see if you can figure out where you went wrong, and get really comfortable with this, because again, these are skills we are going to use today, tomorrow, next semester, for the rest of the year. You will still be using these skills in May, so it's really important that you have them down. Good luck and happy studying!